You go there, Mr.
Absolutely, but.
All right. Yes. You good? You got sound? You got audio?
All right, good go.
All right. Welcome, everybody. How you guys doing?
Hanging in there.
Second, third to last presentation for the show. So thanks for coming. How many people in the audience went to my coworker's presentation yesterday that kind of talked about the upstream electrical architecture? Okay, not everybody. So this is a follow-on to that. We're going to go in a little bit deeper about what's upstream of the rack and talk about the architectures as well as the costs. So this is called a workshop. So feel free to ask any questions as we go along, and I'll take them at the end also. So I'm going to start on the reliability side here. So it's super easy to design on paper an extremely reliable architecture. And that's what has been done in the past. And the architectures have actually ended up being very complicated. But it's really difficult to balance the cost, the required level of reliability to support the applications that you're running, and then usability and maintainability, which actually ends up affecting reliability and then efficiency. And so we want to explore how the open compute architecture affects these. And basically for this work group, kind of propose some things as starting points for folks to do designs and help push the community forward. So yeah, what's in between utility and an OCP rack there with the PSU and BBU? All right, so as we took a look at the architecture, you know, we mapped out what's typically done, and what you see here is a little bit more detail of the typical 2N architecture, right? So UPS is on both sides and all that stuff. And in order to really analyze it, we broke it up into its subcomponents. So medium voltage level, low voltage level. We looked at what we call the pod level. It's kind of not quite final distribution, but close. And then what's happening at the rack level. Okay, and at this point, and at the end, I'm going to show you Tradeoff Tool. It really helped us analyze where costs are shifting and how the architecture changes, where you put energy storage. All right, so you'll kind of see this theme, and it's mostly color-coded pretty well. So, you know, so we stripped it down to its bare minimum to actually pretty much get power to the rack and to understand where the costs lie. So here's the architecture. So the first thing that you noticed in the waterfall chart, if you saw the presentation yesterday, was we removed the redundant low voltage path here. So that you take all that away, and that's a significant portion of the cost that end up going away. Now you still have redundant UPSs and power to your rack. Now, if you move the energy storage or battery backup from centralized and move it down, let's see if you guys can see my mouse here, right down here. So we added the PSU and BBU. So now you have energy storage in the rack there, and so you end up losing all the switchgear and the complexity that we had there. And then another thing that we did in the design that I'll show you here is we moved the backup generator from a large parallel bus up top, and actually took a look at putting it down in the LV, and I'll show you that and why we did that. So this is a very simple architecture. Now, how many people here, I like doing little surveys, are involved with, you know, very, very large data centers? Okay, great. So, you know, depending on the size of your data center, right, do you design the MV, LV, et cetera? So people usually get involved in MV design for data centers that probably minimum is 5 megawatts of IT load. Probably as you get to 10 megawatts is when the designers get involved versus it being provided by the utility. So just understand that if your scope is lower, you can kind of look at LV on down. Okay. So the bare minimum reference design here, and this is the block diagram, and I'm actually going to go to the drawings here. So we did put redundancy at the MV level in kind of a tri-redundant fashion. So so this allows for concurrent maintenance up at the MV level. Then one of these substations, you go down here where you go from MV to LV, and these blocks are in 2.5 megawatt blocks with the IT load being 1.5. So now it's really tier 1 single feed down to the racks here. The energy storage is in the rack. Single LV generator right here at a 2.5 megawatt. And this whole switchboard will basically cover the whole zone. So not only the IT load, which is 1.5 megawatts, but also the cooling load, which should be there. Okay. So now, if the gods favor me, I'm going to give something a go here. All right. So we didn't just do So I'll start at the bottom and work my way up a little bit. So this shows what one full IT room would look like in this design. And this gives you a feel for the design. Is that coming up well? Yeah. So the server rack we specified at 10 kW. It's a 400 volt system, so this would be a European style design, or basically rest of the world. And 3 phases of the rack, and just kind of a couple of things when you look at it, if you really want to cost optimize the electrical distribution. So we're feeding the rack with one 16 amp breaker, which gives you, at least like 10, 11 kW per rack. And it's so that's highly optimized, it's right sized. And you look a little bit upstream, and we have the busway fed by 160 amp breaker. Now we could have gone to like 400 amp busway or higher, but the reason that we did 160 is it allows for a different kind of breaker downstream because the fault current is much lower when you keep it at 160. So you have to be concerned about arc flash and fault current as you get downstream. And then you go upstream and the feeding each pot. Yeah, question?
Sorry to interrupt. I'm noticing there's no current limiting inductor similar to the Facebook design for the world. They incorporate that for harmonic control and power factor control.
Right.
Would you anticipate something like that being necessary?
The hope is that we do not have to do that if the power supplies are designed correctly, that the power factor correction circuit would not put a leading power factor on it if it's lightly loaded. So that's the issue, right? It's lightly loaded generator issue, right?
Well, it's also the harmonics coming back to this single principle.
Right. Right. Because I realize that those are a pretty large cost and a pretty large footprint within the data center to basically fix a problem that's happening downstream with the rectifiers. So if the rectifiers are correct, then we shouldn't have to use those. Yeah. So 25 amp bus duct is there. So 25, why 25, 2500 amps? That ends up being a good sweet spot, especially with switchgear. As you start to get too much larger than 2000 or 3000 amp switchgear, the switchgear, you have to double up the bus bars and it gets a lot more expensive. So again, everything was kind of sized to get the sweet spot and pricing for all these kind of components upstream. All right, so we're just going up another level as we start to get into the medium voltage substation that feeds it. All right, so in the overall design, there's a total of 6 medium voltage to low voltage substations. And so this is, as I kind of explained, it's 32 amp low voltage switchgear. And so this is running at 400 volts, but 3200 amps. And it's fed by a low voltage generator That's 2.5 megawatts. And why do we pick 2.5 megawatts? Is because that's a super common generator that's really cost optimized. You can get them from multiple vendors. So that's, again, another sweet spot for generators. And then as you look at the medium voltage substation, this is actually rated, I'm probably going to get this wrong. The medium voltage substation, the fault current rating is lower. It's not the 40,000 amps, but it's more in the 12,000 amps. And the reason for that, it's a cheaper class of medium voltage switchgear that you want to go for versus the heavy industrial medium voltage switchgear. And then I'm not going to give you the details of this. So this is where we have the multiple medium voltage substations, and then this gets up into the high voltage connection that the utility provides. So this is the design and analysis, and this is again the highly stripped down bare minimum of what we do if you were trying to again pick apart the electrical infrastructure.
So, am I correct in observing that? I mean, I see everything super optimized, but it looks like a very homogeneous example of a data center. Therefore, it seems like this only works if everything is super consistent, homogeneous, and very static in nature, which is not necessarily how reality works. So I'm just curious how that compares.
Yeah, that's right. So we'll get into what we think might be real world examples of how we expect to get deployed. So that's a great point. If you expect to have like 10 kW per rack, very homogeneous loads, this will be really highly optimized and a great price point, but you probably won't end up there, or most people won't anyways. That's a great point. Oh yeah.
To get down to those low volt currents up on the medium voltage side, that kind of implies a higher resistance transformer.
Yes.
So what penalty is being paid for that?
I would have, off the top of my head.
Does that meet the DOE spec?
This is a European design, so I'm not sure if this was designed for the new DOE transformer specs. Right. So it's a trade-off. So you bring up a good point, right? So there's transformer impedance, which you can kind of call resistance, but it's right. And if you have a little bit higher transformer impedance, it lowers the fault current downstream of the transformer, which allows you to purchase more economical electrical switchgear downstream. But you have to balance it with clearing faults and all that stuff. So you can get a high impedance or a very low impedance transformer, which provides tons of fault current, but then you have to make sure that all your gear downstream is really set for any type of large fault current. So it's really this balance that you want to try to hit with that. And so designers are constantly dealing with this. Europe tends to use a bit higher impedance transformers, which limits their fault current, so they can use different set of gear. The engineering community in North America tends to like lower impedance transformers with very high fault current to clear faults, and then you have very high end medium voltage switchgear. Okay, so as Kevin had said in the presentation yesterday, we believe that a tier 3 style data center is still important for most operators, right? Because software redundancy is not widespread to be able to shift loads over in a period of 90 seconds, especially a large amount. Being able to shut down a whole section of your data center to do maintenance is usually not an option. You have to be able to do concurrent maintenance. And also across the industry, you probably know doing hot work is coming out of fashion because of insurance companies, as well as OSHA requirements. And N+1 redundancy is also typically required for more complex components like the generators and UPSs and power supplies. All right, so I'm going to walk through what we believe would be some typical architectures that we would recommend. So this is again upstream. So for large data centers, and rather than having one generator at the low voltage level, if you need a generator redundancy, it gets very expensive to kind of replicate that across low voltage. So putting it at medium voltage allows you to do redundancy across the whole data center. So you can move those generators up to medium voltage. And you'll notice this is kind of an interesting thing that I'd learned over the past few years. So a lot of, so you have your choice of generators at the medium voltage level. You can get a medium voltage generator, or a generator with a medium voltage alternator, or you can get just a regular old low voltage generator and put a transformer to get it back up to medium voltage. And it turns out that because the low voltage generators and alternators are so common, that adding the transformer tends to be a best cost optimized solution, and there's a lot more people who can maintain a low voltage alternator on the generator. So switchboard's rated at 17.5 kV in volts and 1250 amps, and that's the and 25K fault current. And in this example, we have N+1 generators up there at a 6% impedance. So this is the upstream, still all medium voltage. And then now this is getting down into the low voltage, again, still 2N, and this is showing a traditional design with a UPS on one side, and then optionally you can put one on the other side. And again, providing N+1 in the UPS system there. And I'm going to go down to the pod level and the rack level, and you can see how you can mix and match things. So I'll go there next. So this is showing a distribution in the IT space where you have variation on the rack level. So let's say you're deploying, you have traditional gear, and then you want to deploy open compute gear. So what it's showing is, if you back up one, we have a UPS on side A, and we don't have one on side B. So in this case, you have traditional IT equipment, and then you go ahead and you deploy some open compute equipment. So you could choose to just use one open compute PSU and rely on the battery backup on that side, and you're all done. If you want 2N battery backup, you can actually go ahead and deploy a BBU on the other side that does not have a battery and have basically 2N backup on both sides. So this allows you to have mix and match capability right there at the rack level and deploy traditional racks and OCP racks right next to it. If you deploy in larger increments, and you can do it at the pod level, then you can be a little bit more efficient in the architecture. So this is showing one traditional pod. So in a pod, as we found, is typically in the low voltage distribution if you do it at 200, 400 amps or 250, but it might be around 150 kW up to 200 kW chunks. And you can deploy all traditional gear in that 250 chunk and say, hey, the next one's going to be 100% OCP. You do not deploy a UPS in that pod, and you go ahead and deploy PSUs and BBUs for real traditional open compute style IT. And then the last one is the room level. So now you can have larger chunks, and one room could be completely traditional, and another room could be open compute style with no centralized UPS system. They're pretty straightforward. So it is probably this particular architecture that we expect, if there's an enterprise that wants to deploy open compute hardware, this is the one that we expect to be most popular because it allows people to mix and match if they need. Okay, so before I finish with the PowerPoint, I'm going to go over to our Tradeoff tool here. Did anybody get a chance to come to our booth and mess around a little bit with this Tradeoff tool? All right, so we'll do it here. So as we analyze the architecture and the cost of server power supplies and the cost of PSUs and BBUs and everything upstream, we wanted to understand what its impact was on the electrical architecture. So I'll go through a couple of examples here. So if you go to our website, you can get to this tool, but we'll go and pick a couple of architectures. So first, I'm going to take a traditional 2N. So this is kind of what we showed originally: gen sets, medium voltage gear, and then 2 UPS systems with all the switch gear and everything down to a traditional IT load. And here we'll have a simplified 2N for mixed IT loads, which is what we recommend: 1 UPS and the PSUs at the end. So those are the two scenarios we're going to look at. If you want to look at them in more detail, you can hit this and see slightly better detail. So there we go. Now, the power supplies, so this was kind of interesting, and Kevin talked about this a lot. Getting an accurate feel for what power supplies cost and how much we're oversizing was tough. So this tool is based on a default of 7 cents an IT watt of power supply with a 2N with an oversizing of 3. When we talk about the cost of a data center, I want to make sure we're all on the same page here. So when I say, hey, this stuff costs $2.50, what that means is if you have a megawatt of IT load in your data center, this stuff, the electrical stuff, is going to cost $2.5 million. And this cost is not installation and everything else. It's just the electrical hardware stuff. Does that make sense? 277. Thank you. All right. So now let's dig into this a little bit. So what this is saying is that if we take a traditional, fully loaded, belts and suspenders traditional, that $2.77 versus $2.25. So the open compute, the savings that you get is about 18% just on the electrical system hardware all the way through the server power supply. Okay. And if you want to know where that savings are, so you can kind of dig into each one of the things here. So starting at the top, this is pretty straightforward. If you go to medium voltage level, it's going to be pretty similar. There's not a whole lot of difference between the architectures. You go to low voltage. And so here you see the big difference in, you had a UPS because you have 2 in UPS. In this case, you have 1 in, so it's nearly half. And the cooling distribution changes a little bit. And so in this case, you can see that the UPS is 30 cents per watt. How's that sound? There was a reason you asked that question. All right. So online, and you can play with this afterwards. But so if something doesn't seem right, we're extremely happy to get feedback. So please don't be shy. Yeah. I mean, if we can definitely have a conversation on where we got a lot of no problem. And let's go to the the IT is going to be very similar. Let me go to the rack level. All right. So the rack level, you see the cost change you have in the traditional. There's obviously no power supplies because that's in the IT level. Here you see the issue there in at the rack level. All right, let me just change it to. You want to see the largest difference. If you do this to this, you get a 25% change. And the purpose of the tool is to give you generally, we feel like the level of accuracy, these trade-off tools, we have probably 13 different trade-off tools that go everything from efficiency to data center cost to things like this. This is our latest one that are probably like within 20% accuracy. They're not, if an engineer were to sit down and do a full design and specify the price, should be close, but that's going to be really accurate. This will get you when it's probably plus or minus 10%. But I don't know, is that price savings about what you guys would expect if you were to deploy an open compute, or did you have no idea? I'll take that as a.
It's got to be way cheaper.
What's got to be way cheaper?
It's way cheaper than traditional. I mean, that has to be. Right? You're looking at less than a quarter.
Well, this is the most extreme example that we could come up with. Right? So this one, 45% for a full old style, traditional architecture to a stripped down OCP. The most common comparison we believe is really traditional. And even if you do a simplified, if you do a simplified architecture, both traditional and OCP. The difference is a lot less, but it all does depend on in your mixed open compute one, if you have some traditional, some open compute, if you change that to zero traditional, more open compute, you can see the savings goes up a little bit, so you can play around with that. So, so there's a couple of supporting materials that we have behind this. First, there's the reference design that we did of the strip down, and again, it's if you're interested in looking at that, we can send it to you. It's everything with AutoCAD and electrical one lines. It has the cooling system and piping diagrams and things like that. We have this trade-off tool. We also have a white paper behind us, 228, which is talks about this. We also did some analysis on lithium-ion batteries recently because we just announced that. And so we have a trade-off tool on that, and 229, and you can get these at the 2 URLs there. So, so the takeaway after we did this study is a couple of things, right? The stripped down low-cost architecture is limited in application. We don't expect too many people to do that. Tier 3 architectures can be very easily adapted to support the very methodologies of mixed load deployments, which we think is going to happen as open compute gets deployed or adopted. And the open compute benefits and cost savings on the power side can be realized, you know, even if you are starting with a traditional data center and you're kind of transitioning over. And, you know, hopefully the work we've done helps get the data center work group going, right? We get some more participation and stuff like this. And I think Jason would agree there, right? So I'll open it up to questions.
We have about 20 minutes. If anybody has any questions?
Oh, and this was supposed to be a half-hour slot, so I don't know how it turned into an hour, just to let you know. I had prepared for a half hour.
Well, with our video difficulties, I think you kept it within your.
Yeah.
Any questions for Bob? All right.
Skeptics, no skeptics with this stuff?
Before you guys leave.
Well, one's gone.
All right, go ahead. Don't anyone else leave yet, please. But if there are questions, please ask Bob.
Yeah. No, we very much appreciate any folks that disagree with with our findings, because we're looking to make sure that data is as accurate as possible.
Well, I'll raise a question then. Are you seeing any adoption of an open compute infrastructure in a traditional data center? A lot of your comparisons were one to the other, but in my mind, so far I've seen it. You have traditional data center, and then you have open compute in places like Google.
Right.
What are you seeing in the field?
So if you take, we'll take co-location, they're going to be pretty traditional because the expectation of their customers is pretty much to have battery backup on both sides and pretty high SLAs and stuff. So there hasn't been too much there. There has been optimizations in the electrical infrastructure and some prefabrication that those guys are doing, which is making it more cost effective. There is more and more talk of optimization of the tiers and getting those costs down, but it's not moving as fast as we would expect.
Are you seeing anything in, for instance, like a university setting where they might be trying to do some work and some papers and some research on this? Power differences.
Most of the work you see happening in universities is definitely on the power conversion side, the whole AC to DC thing and things like that. So you see that a lot, and obviously we've done a lot of work there too.
Thank you.
Yeah.
Thanks, Rob.
Thank you.
So the first thing I'll implore everyone to do is to join the mailing list. And when someone says mailing list, I can almost hear all the eyes roll because like, really, more email. But this is the way that we communicate within the data center group and really all groups within OCP. So that's the first point. So if you want to be involved in the discussion, any ideas or just lurk, right? Just read, you don't have to say anything. this is how to do it. This is how I communicate when meetings are, if they change, although it's the third Thursday of every month, 11:30 Eastern. But you can find that on the wiki. The other thing I'll say is you won't get any spam. The reason I know you won't get any spam is because I have to deal with those. So it's a moderated list, and the volume of emails that come through are not really all that high right now. So please, 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 before you leave even, sign up for the mailing list. And the other thing is I have the little red box there. Please choose no to the Daily Digest, because if you choose yes, you will only get an email at 8 a.m. Eastern roughly every day. And so this is a problem if for some reason a meeting has to change and I send it at, say, even if I send it 8:01, you won't know till 8 o'clock the next day, Eastern. So anyway, that's the one point I want to make. I was going to put useful links here, but really, I don't want to like inundate everybody with links. This is really the only link you need to know, because all the useful links will be on the wiki. It has when the meetings are, how to get to the meetings, the specs under review, the existing specs, and all that stuff are on the wiki. So just to give a rundown of the current specs on the wiki that are available for review, some of them have been there for a while. But anyway, this is what you'll see if you look at it right now. There's a DC power spec. I'm guessing that probably might see a revision. You think? I'm looking at John back there with EDCS. And then the data center operations maturity model that was submitted by Schneider. This is just a recap of some of the things that have been discussed in previous meetings. For those who haven't been involved before, we talked about the concept of an open row. I think a lot of the reason we haven't seen a whole lot of progress in participation is because we've tried to take too big of a bite, right? Okay, let's take the data center design that Facebook gave and let's iterate on it. And I think that's a little too much. So we took a step back and said, okay, well, let's think about it from a lower level perspective. What can be useful for the market out there? So the open row was one idea. I can't share a whole lot on the next one just yet because it was based on an email I got yesterday from a supplier of prefab data centers that he is interested in bringing forth a submission for an OCP ready submission for prefab. It isn't really container based. That's all I can really share about it right now. But stay tuned on that. So you should see some discussion in the mailing list probably pretty soon on that. And then a rough idea on point components, for example, UPSs, PDUs, switchgear, whatever. Those are some ideas that that might be helpful for the discussion in the group to go along with and tie very closely to the rack configurations and all of that. And I mean it. Join the mailing list. I'm not kidding around. And that's it. So, I mean, I'll take questions, but probably aren't many. I apologize for there not being a dedicated data center track this time around. There were so many submissions for presentations that I couldn't do it. One of the things that we really need to nail down, you might be surprised, we don't actually have a charter for the group. There's been some progress on it, and there is a draft out there right now. I will shoot out an update on that to the mailing list probably in a few days to give everyone a chance to sign up for it and get all that worked out. So look for that. But because of the time constraints, we had no dedicated data center track. Not this time. Hopefully that'll change in the next summit. Anybody have anything for me? I guess I should have said that I'm the project lead. I neglected to mention that, but I'm the project lead for the data center group. All right, thanks. And I think we have,
2 o'clock.
yeah, 2 o'clock. What time is it right now?
It's 1:45.
Okay,
15 minutes.
so Rugged Pod should be back here in about 15 minutes or so.